Our topic of discussion is dielectric and the effect of inserting a dielectric within the plates of a capacitor. So a dielectric is neither an insulator nor is it a conductor. Dielectrics are more or less similar to that of an insulator, but in an insulator there is no movement of electric charges. However, the difference between an insulator and a dielectric is that if a dielectric is placed in an external electric field, then in the presence of that electric field, there is a rearrangement of the electric charges within the atoms of the dielectric. So, whenever a dielectric is placed in an external electric field, the molecules of the dielectric, which may or may not possess a net dipole moment, the electric field will always try to arrange the dipoles in the direction of the electric field, in the direction of itself. So, for the time being, if we assume that the molecules of a dielectric, they are having a permanent dipole moment or a net dipole moment, then in the presence of the electric field, the dipoles will all experience a torque, and that will try to align the dipoles along the direction of the electric field. So what happens is that if a dielectric slab is placed in an externally applied electric field, let me call that externally applied electric field as E0. So the dipoles are experiencing a torque, and due to the rotation of the dipoles, due to this torque, there is an apparent sheet of positive charges and a sheet of negative charges on the faces of the dielectric slab. So whenever this separation occurs, this apparent sheet of positive charges and sheet of negative charges is due to the fact that in the presence of the external electric field E0, the dipoles have all aligned themselves along the direction of the field, and they have created a net field that opposes the original electric field. So what we are trying to realize is that the apparent sheet of positive charge and the apparent sheet of negative charge, which can be also called as induced surface charges, this apparent sheet of positive charge and this apparent sheet of negative charge, they appear on the faces of the slab, and they can be called as induced surface charges because they appear on the surface of the dielectric slab. Surface charges. Now these induced surface charges will create a field that will oppose the original electric field E0 vector. So this field might be called as EP vector, and this field is also called as the polarization field. And now we say that the dielectric has got polarized. So what happens is, suppose there is an external field. Suppose we have two plates of a capacitor. Suppose this is the positively charged plate and this is the negatively charged plate. So if you place a dielectric slab, what will happen is, obviously this positive and this negative charge will create a field. This field is the externally applied externally applied electric field E0 vector, and within this plates a dielectric slab has been introduced. Surface charges that will appear on the dielectric is such that it is always opposing E0 vector. So charges that are getting induced will be of this form within the dielectric. It will create a field EP vector that opposes E0 vector. So the net field within the dielectric will now become net field inside the dielectric now E vector, which is the vector sum of both the fields E0 vector and EP vector. But we see that the polarization field EP vector is opposite to E0 vector. We can say that the magnitude of E is E0 minus EP. Hence, the dielectric has reduced the field E0 to the value E. So that is, you can say that now the field within the dielectric is E, which is obviously less than the externally applied electric field. So when a dielectric is placed in an externally applied electric field, the induced surface charges appear that tends to weaken the original field within the material of the dielectric. So if E0 increases, simultaneously EP will also increase. So we can say that this EP is proportional to E0. We can say that this EP is proportional to E0 because if E0 increases, EP also increases. And from this relationship E is E0 minus EP, we can also say that E is proportional to E0 because the rate at which E0 will increase, it will obviously increase EP, and therefore that will alter E. Now we can introduce a constant in this proportionality relationship, and that constant is 1 upon K, where K is called as the dielectric constant of the dielectric. K is called as the dielectric constant of a dielectric. Now this dielectric constant is a characteristic property of the dielectric. It does not depend upon the shape and size of the dielectric. It is a characteristic property. It is dependent on temperature, much like resistivity and conductivity. It is a characteristic property which is temperature dependent only. So the net effect is that the presence of the dielectric has reduced the externally applied electric field because the dielectric gets polarized in the presence of the externally applied periodic field. Now sometimes there are dielectrics which are polar by nature or which are non-polar by nature. Whatever type of dielectric we take, the effect of the externally applied electric field is to induce surface charges on the dielectric, and that induced surface charges will create a polarization field that will oppose the originally applied electric field, and thereby the net electric field within the dielectric will get reduced as compared to the initial electric field that was being applied. So dipoles or the molecular dipoles, whatever we say, of any dielectric are always in random thermal motion, and this random thermal motion might destroy the alignment of the dipoles, but it is the externally applied electric field which will again try to rearrange or align the dipoles along its own direction. So we come across different types of dielectrics. Either the dielectric is polar or the dielectric is non-polar. So in case of polar dielectrics, the molecules have a permanent dipole moment. But in the case of non-polar dielectrics, the molecules do not have a permanent dipole moment. So if we classify a dielectric, we can say that either it is polar or it is non-polar. Examples of polar dielectrics might be water. Example of non-polar dielectrics, not only water, there are many such examples. Carbon dioxide can be considered as a polar dielectric. NH3 can be considered as a polar dielectric. Non-polar dielectric, more or less the symmetrical molecules like H2, N2, O2, these are all non-polar dielectrics. So polar dielectrics, they have a net dipole moment. The molecules have a net dipole moment. Net dipole moment, whereas in the case of non-polar dielectrics, the molecules do not have a net dipole moment. But however, in the presence of the externally applied electric field, the dipoles will tend to align themselves along the direction of the field, and that will reduce the externally applied electric field. Ultimately, whether it is polar or whether it is non-polar, it will get polarized in the presence of the externally applied electric field. So, we can say that the atoms of either polar or non-polar dielectric, they can be considered as spherically symmetric cloud of negative charges. The atoms of polar or non-polar dielectric can be considered as spherically symmetric cloud. Symmetric cloud of negative charge, that is the electrons surrounding the positively charged nucleus. The positively charged nucleus. What happens in the case of polar dielectric is that the center of distribution of these positive charge and negative charge, the negative charge means the symmetric cloud of charge, the center of distribution of the positive and the negative charge, they do not coincide, and so they have a net dipole moment. Whereas in the case of non-polar dielectrics, the center of distribution of the positive and the negative charge coincide, and so they do not have a net dipole moment. So you can say that the center of distribution of positive and negative charge do not coincide in the case of polar dielectrics, whereas in the case of non-polar, the center of distribution of positive and negative charge coincide, and so they do not have a net dipole moment. So, if we apply a large electric field to the dielectric, then we can ionize its atoms or molecules and create a condition for the electric charges to ultimately flow. Then it behaves like a conducting material. So in the presence of a sufficiently large electric field, the atoms and the molecules can ionize, and then the charges start to flow on the surface of the dielectric. That particular field at which this breakdown occurs is called as the dielectric strength of the dielectric. So you can say that the dielectric strength is the maximum value of the dielectric, the maximum value of the externally applied electric field that can be applied without causing dielectric breakdown. So if a sufficiently large electric field is applied to the dielectric, the molecules and atoms the ions, and charges begin to flow on the surface of the dielectric. So this is called as dielectric breakdown. Now the dielectric is no more showing the properties of a dielectric. It is now behaving like a conducting material. So it is called as dielectric breakdown. And therefore the maximum value of this electric field for which the dielectric breakdown does not occur will be called as the dielectric strength. Strength of the dielectric. So you can say that it is the maximum value of the external field applied electric field for which dielectric breakdown does not occur. Does not occur. So now we try to realize what happens when a dielectric is placed within the plates of a capacitor. We will see that the capacitance of the capacitor will increase in the presence of the dielectric. Suppose we have the plates of a capacitor on which charges are already present. A dielectric slab has been introduced. Suppose the distance between the plates is small d and the thickness of the dielectric is suppose small t. The plates were initially charged. Suppose this is the positive plate and this is the negative plate. Surface charges are induced on the dielectric. The induced charges will create a field that will oppose the original field that we have already discussed. And this field is the polarization field, polarizing field, EP vector, and the original field was suppose from the positive to the negative plate in this direction. and this is E0 vector. Along this direction. So suppose the charge on the capacitor plates was initially Q, plus Q and minus Q, and the corresponding surface charge density was plus sigma and minus sigma. The area of the plates, the area of the cross section of the plates is suppose A. So obviously sigma is Q by A. In the absence of the dielectric, the electric field E0 is obviously sigma by epsilon 0, which is Q by epsilon 0A. In the presence of the dielectric, the field has reduced and the field within the dielectric is now E, which is obviously E0 minus EP that we have already discussed. And we have already realized that E is equal to E0 by K, that is the dielectric constant of the dielectric. Now, the potential difference between the plates in the presence of the dielectric will be the potential difference between the plates. In the presence of the dielectric. Suppose capital V. Now we can realize that there is some space where the dielectric is not present and there is a region where the dielectric is present. So in the region where there is no dielectric, this potential difference is obviously the electric field E0 into the distance or the space of that region. So if you realize the diagram, then you can say that D is the distance between the plates, and in the region D minus T, that is this specific region and this specific region, there is no dielectric. So the potential difference will be E0 into D minus T in that region. Because in the space D minus T there is no dielectric. This region and this region refers to D minus T. And there is no dielectric, so the potential will be E0 into D minus T plus the region of the dielectric where the electric field has modified to E. So E into T will be the potential in that region. So now E0 into D minus T, instead of E we can write E0 by K. If we take E0 common, we get D minus T plus T by capital K. So if I take common as T, this becomes D minus T times of 1 minus 1 by K. So now V becomes E0 into D minus T times of 1 minus 1 by K. Now we will replace the value of E0 as Q by epsilon 0A. So this is now Q by epsilon 0A into D minus T times of 1 minus 1 by K. So this is what we get as V, the potential difference between the plates in the presence of the dielectric. Now if I write it as Q by V, I will get Q by V as epsilon 0A divided by this factor, that is D minus T times of 1 minus 1 by K. Now what is charge by potential difference? Definitely it is the capacitance of the capacitor. Now this Q by V I can write as C. This is the new value of the capacitance in the presence of the dielectric. So this becomes epsilon 0A divided by D minus T times of 1 minus 1 by K. So this is the capacitance of the capacitor is in the presence of the dielectric slab of thickness T and dielectric constant capital K. D was the original separation between the plates and T is the thickness of the dielectric. Now what we realize is that this value is of C is definitely greater than the initial value of the capacitance when the dielectric was not present. So you can say that in the absence of the dielectric, the capacitance was epsilon 0A by D, which we can write as C0 as epsilon 0A by D in the absence of the dielectric. Now in the presence of the dielectric, the new value of the capacitance is C equal to what we have got here, epsilon 0A divided by D minus T times of 1 minus 1 by K. Now from the denominator, if I take D as common, I can write it as epsilon 0A divided by D. I am taking D as common in the denominator, and this becomes 1 minus T by D times of 1 minus 1 by K. So epsilon 0A by D is obviously C0. So C is equal to C0 divided by 1 minus T by D times of 1 minus 1 by K. So obviously the denominator is less than 1, which means that the capacitance of the capacitor has increased. C0 divided by a factor less than 1 is obviously greater than the initial value of C0. So therefore you can say that C is greater than C0 by this factor, which is 1 minus T by D into 1 minus 1 by K. Now if you say that if the entire space of the plates is replaced by the dielectric, if the entire space consists of the dielectric, entire space between the plates of the capacitor is the dielectric slab itself. The thickness is 0 because it covers the entire space of the dielectric. So definitely this T becomes 0, and therefore what we have is C equal to epsilon 0 if the entire space consists of the dielectric, then T covers the entire space, that is T is equal to D. So therefore in this expression you see, or in this expression you can see that C equal to epsilon 0A divided by D minus whichever expression you take, let me take this expression. C0 divided by, instead of t I will write d. So 1 minus d by d times of 1 minus 1 by k. So d by d is 1. So 1 minus 1, 0. Minus of minus is plus. So what we get is C equal to C0 into K, which means C equal to C0 is again epsilon 0 A by D. So this is epsilon 0 A by D times of K, which means C equal to epsilon 0 K epsilon 0 A by D. So this is the situation when you simply say that the entire space between the plates consists of a dielectric, or you can say that the plates are kept in a dielectric of dielectric constant K, or in a medium of dielectric constant K. So this is a special case of this one.